Hi, Bobby.
Hi, hi.
So let's continue with our discussion on, we were discussing
Amplifier.
amplifiers. Exactly, right? So, right? So we basically, we were discussing the following, right? We abstracted out the amplifier, right? And we said you have a gain, you have a V in of T, and you have a V out of T, right? So we said that if the input is some frequency like this, then the output was in phase with the input, and we were able to get an output signal like this.
Scaled version.
Exactly, right? So this is, I'm going to plot in red. Okay, and V out of T was equal to some
A times
V in of T. And in the last experiment, we had set A to be 10. Okay, so if this was
1 volt
or 1 millivolt, let's be 1 millivolt, then this happened to be 10 millivolt. Right, this is what we had seen, and of course we were looking at the case where we were able to do addition followed by But I think in this lecture, let's look at just a simple single sinusoid, okay? Because we want to understand the amplifier a little better in more detail, but without going into the internal details. Okay. So first of all, this in phase, output, right? So have you come across a scenario where you need something which is not in phase?
Yeah. Sometimes I may need something at 90 degree or 180 degree.
Okay, or 180 degree away, right? So essentially, if it is 180 degree, you're basically saying that you want the sine wave to be off by half a period.
Yes.
Right? So in which case, the sine output will look like this. Correct?
Exactly.
Right? So let me just...
It will look like, it's an inverted version of
the
what
red,
you had earlier.
Of the red wave, right? So the amplitude will still be, this minus 10 millivolt, plus 10 millivolt and all that. The frequency is not changing, but it's only the phase that has sort of moved, right? So this is called essentially an inverting
amplifier.
Yes, inverting amplifier. The amplifier that can produce such an output is called an inverting. The amplifier that produces the red one is obviously a non-inverting amplifier, right? So in today's experiment, what we have again is, the same amplifier that we had last time, okay, along with two resistors that are, tunable, okay,
used to set the gain,
used to control the gain. Exactly. So there are two resistors, that R3 and R4 together will sort of tell you what the gain of the amplifier is. Okay, we'll not worry about this function. One of the resistors can be tuned and the gain can be controlled. Okay, and this A is a negative number.
Oh, that's how you are getting the inversion.
Exactly. Okay. Right. So the minus. So if I give V, if my V in of T is 1 millivolt sine of omega naught T, then my V out of T is going to be minus 10 millivolt sine of omega naught T. Sorry. Right. So it's essentially going to be a negative number, right? So the A will be minus 10 in this particular case.
Understood.
Okay. So of course, in this experiment, the values that have been chosen is the resistors are, you can get a gain of up to minus 5. Okay, it doesn't go all the way to minus 10. But I think let's go ahead and see, what happens now. Okay. So what we are going to do is, as usual, we are going to look at this particular oscilloscope.
Full screen
and a signal generator, right? Let's make it full screen, you're right. And as usual, we are going to give an input signal which is a sine wave.
So this is the function generator output.
This is the signal generator or function generator.
Okay.
So it's a 500 millivolt, right? So maybe I'll make it 100 millivolt.
Yeah.
100 millivolt, 1 kilohertz input.
Okay.
Right?
Is given to this.
Is
amplifier.
given to the input of the amplifier, and the output we are going to go and look at it on the scope, right? It's, you know, there is a certain range. So let me make this as how much?
100 millivolt.
100 millivolt per division. Channel 1, channel 2.
Same maybe.
Yeah. Okay, this is, you know, good. It's very
so
clear.
it's inverted.
Exactly. Right. So what you see is, as the blue input, right? Blue is the V in of t. The orange, as usual, is the V out of t. As the input goes into its positive half cycle, the orange one is going through the negative half cycle.
So that's how the minus A plays.
Exactly, right?
Okay.
So the gain here, what is the gain? This is 100 millivolt. The output is about
close to 3 point
3
something.
point something. So,
yeah.
So there is, as you can see on this board, there is a pot.
Variable resistor.
Variable resistor. So can you just tune that a little bit? Let's see what happens.
I will change this a little bit.
Very good,
okay,
right?
Okay.
This is nice. So you're seeing,
I'm able to change the A.
Exactly. So you're changing the resistance, right?
Okay.
And
so now it may be 1, 2, 3, 4. 4. Yeah.
You've got it to a point where the gain is about 4, minus 4.
Okay.
Right?
I
and
can
if you
do the other way also.
Yeah. Let's go down and see.
Okay. Now it's 3.
It's about 3. Maybe let's sort of leave it at this point.
Yeah.
Right? So you have, what you have done is, you basically set the gain of this amplifier equal to minus 3, right? By adjusting that resistor out there. Okay. So now what we want to do is, we want to analyze this amplifier a little further, right? So for example, what do you suppose will happen if I increase this 100 millivolt to 200 millivolt?
The output will also scale accordingly.
Okay. Right. So let's go ahead and check that out. I'm going to say, let's make this 200 millivolt.
So input is doubled now.
Input is doubled. So the input amplitude is 200 millivolt. The gain is minus 3. So therefore the output should be about 600. Right. So I have to make this 200 millivolt. Let me make both of them 200 millivolt.
Yeah.
Okay.
Yeah, it's coming correctly.
It is exactly about 600 millivolt, right? And you can see that both of them are still valid sine waves. Okay.
And they are still in 180 degree.
Exactly. So let's make a table here. Okay. I'm going to just talk about what is my max of V in. Okay, so the V in has an amplitude, right? So I'm going to look at that max value, and I'm going to look at the max of V out. Okay, this is the peak value of the input and output.
Okay.
Okay, and we'll also say, is it sinusoidal or not? Okay, and we'll also observe the phase. Okay, so we saw earlier, if this was 100 millivolt, that you had set the gain to 300 millivolt.
Yeah.
Okay.
Sinusoidal, we can put a tick maybe.
Absolutely. Both of them indeed looked, and the phase was 180 degrees. No problem. Then we doubled this, the input to 200 millivolt, and we got an output of 600 millivolt. Right? It was sinusoidal, phase still remains 180 degrees.
Yeah.
Okay. Now, let's go ahead and continue with this process. I'll make it 500 millivolt and you expect the output to be
1.5.
1.5 volt, right? And of course, it's all going out of scale because this, right? Nearly
Yeah.
1.5 volt.
Yeah.
The input is obviously swinging between minus 0.5 and plus 0.5.
Yeah.
The output is nearly, so this is 500 millivolt, nearly 1.5 volt. Okay, I won't say it's exactly because it is not getting there. It's nearly 1.5 volt. It is sinusoidal reasonably and the phase is still 180 degrees. Okay, now I'm going to continue this.
1 volt.
I'm going to say 1 volt.
Okay.
What do you expect the output?
3 volts.
3 volts. 1 volt per division, 1 volt per division, and
Nearly 3 volts.
nearly, right? Nearly 3 volts. 1 volt, nearly 3 volts, sinusoid, and 180. I think that is not, that hasn't changed as yet.
Now we will make a bigger jump.
Go for a bigger jump, right? I want to make it 2 volts.
Okay.
What do you expect the output to be?
So still,
3 times.
yeah.
6 volts.
Yes. Should be. Oh.
What do you see here?
It's no more sine wave. Its head is gone.
It is gone, right? So that's an important observation. We said 12 volts.
2.
2 volts,
Yeah.
sorry. The maximum amplitude is somewhere near what? 4.12, 4.2
Okay.
volt. 4.2 volt, okay? It is clearly not sinusoidal. The phase is still intact. It is 180 degrees.
Yeah,
in the sense,
but it's no more a sine wave.
it's
so
not a sine wave anymore.
Yes,
It's
yeah.
got distorted.
Yeah.
Okay.
Yeah.
So now what we
So,
have?
but what happened?
Exactly.
So far, it was good.
It was good, right? So let's just look at this. You know, even the picture that we drew. Okay, V in, and we said V out. The frequency of the wave is not changing. I think even when it is distorted,
Zero crossings are at same point.
exactly, right? The periodicity still remains as it is. So there's nothing to worry about in terms of the frequency as yet. So there is one peak value, V peak of input, right? Which is what we plotted in column 1. There's a V peak of output, okay? And it seemed that changing Vp in affected Vp out, and that's all there was. There was
Yeah.
no other factor
Correct.
that was going to affect this. So now the question is, will this, you know, this behavior of
Yeah.
going to stopping at 4.2 volt, is that always 4.2 volt? Where did that number come from?
Yeah.
Why did it stop at 4.2? Why not 5.2? Or why not 3.2? Right? Or 2.2? Right? So there is an other magical control which is deciding this. Okay, so let's first do the experiment and then we'll come back to the theoretical understanding. That's
Okay.
called the power supply,
Oh.
right? So we'll understand why we need this supply later. Okay, there is a V plus and there is a V minus
Okay. Okay.
to this amplifier.
So this amplifier requires some additional power supply.
It requires an additional supply. So the theory we will discuss a
It's
little
a
later.
DC power supply.
A DC supply, right? I'm going to now set this to 4 volts and minus 4 volts.
Okay.
Okay, earlier when we did this
It was
experiment,
5.
V supply, okay, V plus equal to minus of V minus was 5 volt.
Okay. Now you have reduced.
I have reduced and we saw that this guy was saturating at some 4.2 volt. I want to see what's going to happen now.
Oh.
Okay, if I repeat this experiment.
So it may happen at even lower voltage.
Exactly. There you go.
Oh. You reduce our input voltage?
I did not do anything to the input voltage.
Oh.
Okay.
Okay.
I've just, in fact, I will but let's just note this value. If the input was between V peak was plus 2 volts and the supply was reduced to plus 4 volt.
Now it is 3 point something.
Yes, on the positive
Okay.
side, right, this guy is saturating at out here 3 point some 2, is it? 3.2 volts.
Yeah. So I cannot have large amplification like I wish.
Exactly.
It also depends on the power supply voltage that you are giving.
Exactly. In fact, we can also, let's try one more thing. What if I make only the negative as 0 or minus 500 millivolt? So this is,
Maybe you have to stop and see.
no, I think, yeah, but this is sort of too asymmetric. So what if I make it minus 2 volts? So there seems to be some clipping happening on the negative side. The positive side is going up. Right? So I will take this back symmetrically to minus 4 volt and then I will run it. And then we are able to see this. Right? So there is, in some sense, a little bit of independent control on the positive side and the negative side. Right? And if I lower this further, to minus plus, instead of 4 volt and 3 volt, what if I made it 2 volt? Right? Or maybe 3.5 volt. Minus 3.5 volt. It has dropped further.
Can we reduce the input and see is it still working?
Yes, that's also a great thing. So I'll just make a note of this before I proceed. This was saturating at 2.7, right? 2.7 volt, right? What is it for 4 volt, right? And this was 3.5 volt. Sorry, in pink, right? 3.5 volt. But now let's do the experiment that you said, right? Now, if I bring down this particular input amplitude back to this 100 millivolt range,
or even 500 millivolt.
Let's start with 100. We'll go back. Right?
Oh, it looks fine.
It looks fine. It looks absolutely fine.
Okay.
You see,
so this amplifier is still working.
Exactly. The amplifier is still working. The sinusoid remains a sinusoid as long as you don't get to that power supply, near the power supply.
So the output voltage should be less than the power supply voltage.
Exactly. The output swing, right, as they call it, should be a little away from the power rails.
So when you say swing from the minus to
negative
peak to positive peak.
Minus my negative peak, the most negative value should be far away from the V minus, and the most positive value should be a little far away from the V plus, essentially, right? Now we can try whatever you said here. Okay, we'll make it 500 millivolt and we'll see what happens here.
Still okay.
Right? It's not bad at all. And remember, the amplification is still the same. Just because we reduce the supply, it doesn't mean that this amplification is gone. That is still the same factor of 3 that you had set by adjusting that resistor at 5 volt, right? So that aspect remains the same as long as you are not close to the supply rails.
Understood.
Right? Now, let's just go to another interesting thing, right? Before we analyze why this is the case. Okay, let's first look at a simple voltage divider. Okay, I have an input here, a ground, and I'm applying V in of t, and I'm taking V out of t here.
Okay.
Right? Now this V in of t, okay, V in of t, and the relationship between V in and V out. V out of t is obviously R2, if this is R2, by R1 plus R2 into V in of t, right? So there are two, signals with different energies actually, right? So there is an energy associated with the input and there is an energy associated with the output. Okay, if these two are sinusoids, right, then the energy can be calculated. If you remember, we did the RMS calculation, right? Just V RMS squared by 2, right, into the time, effectively into whatever time we are looking at. So if you look at the RMS value of the voltage, we will get a estimate of the power and energy. Okay. Now, can we say that, energy input and energy, what do you think the relationship between these two should be?
I don't know.
Okay, so can E out be greater than E in?
E out be greater? I doubt, because you have a resistive divider and you have lower voltage as the
So
V
exactly.
note.
So the scaling itself seems to suggest that E out, right, this has to be true.
Yeah.
Right. Now, even otherwise, as an engineer, not just as an electrical engineer, energy has to be supplied from somewhere. It can neither be created nor destroyed, right? Energy is conserved, right? So at most you can convert one form of energy to another, and the moment as an engineer, you see energy going up somewhere, the first question is, where did that energy come from, right? Now here it's very clear that E out is less than E in. So at most some energy can be lost, and where is it being lost? Of course, as
in resistors,
in the resistors as heat, right? So therefore there's no problem here.
Yeah, agree.
Now we look at the amplifier case that we had. Okay, this was our input. Okay, whether you take an inverting amplifier, okay, or a non-inverting, the energy will not change because VRMS, right, you are squaring something, so it doesn't change, right? If you take this signal, right, okay, this is not a good drawing.
So here you have more voltage.
I have more voltage in my output, right? And therefore I have E in and E out, but it appears that E out has more energy than E in, right?
That's how you are able to drive that 1000 watts.
Exactly. That 1000 watt speaker we were able to drive by actually pumping in more energy. It's not that the musician is singing so loud such that the speaker is able to actually do it, right?
So the mixture is not giving that much energy.
Mixer is not giving that much energy.
But amplifier is giving out.
Exactly.
Large energy. So from where is it coming?
Exactly. So that's the exact question that we want to address now here, right? So in the previous discussion, we saw that there was a third control parameter that decided the amplitude of this wave.
Some silent guy.
Right? Okay. Exactly. So we had an amplifier, okay, and we had the V plus and V minus. So now we have three parameters, okay, which can supply current as a function of time and all that. And therefore, if you want to look at it from an energy perspective, you have to look at the energy of the entire system.
Okay.
And therefore, I will call the energy of this V plus and V minus as EDC.
Okay.
Okay. And now I can write EDC plus input voltage, because somebody is generating that voltage for us, right? This should be greater than E out.
Okay.
Right. So in some sense, the amplification is okay as long as the DC source can provide that energy. And that's why the sinusoid was also intact. Okay. It was intact. But beyond the point when we started, pushing the input, the E out to remain a sinusoid needed much more energy than what the DC supply could give, and therefore it simply got clipped. Now, where exactly it clips, it depends on the internals of the amplifier. We will not go into that.
Yeah.
But just as an energy argument, it's possible to sort of appreciate that the clipping phenomenon that we actually saw in the in that table, right? And that's why when we started lowering this, VDC, we made from 4 to 3.5, 3 to 3.5 to 3. We also saw that the amplitude of that sine wave started clipping earlier, right? Essentially, the DC supply is not able to provide that energy.
So whenever there is a electronic amplifier like this, there is a power amplification also.
Exactly. There is a power amplification. It's not just voltage, it is the energy that is actually being amplified, right? And that energy is coming from some other supply source, right? Here, I did not need that extra source because I am taking it from the input and actually just scaling it down.
Yeah.
Right? I don't have to worry about adding energy to this particular system here. And therefore, it was okay. R2 by R1 plus R2, as you said, is obviously a number less than 1. It has to be lesser energy, and therefore, we were fine.
Yeah.
Okay. So, that sort of, in this first course, without understanding transistors and all that, I think this will limit how much we can understand about an amplifier.
Yeah.
But, effectively, it is true that the sinusoid will remain a sinusoid up to a certain point. After that, you will start seeing some distortion, clipping, and stuff like that.
How good a sinusoid will be also depends on how good the amplifier will be.
Exactly. And in fact, in your laptop, if you take and in a VLC player specifically, there is this 200% amplification, which is not good for your speaker because you can actually hear it clip beyond the point. There's a sound, right? That basically means the speaker is clipping, which means the amplifier has produced an output that is saturated, right? And the signal is sort of becoming more infidel.
So saturated, you mean this
clipping?
Yeah.
Exactly. It is sort of saturated. Essentially the output has saturated and just remains at that particular value. All right. So, the next question that I really have, and we also discussed it when we discussed the non-inverting amplifier, right? This omega naught. What do you think will happen?
The highest frequency I can operate.
Frequency, we increase it, can the output. So essentially what we are saying, right, in this particular case is the input is going reasonably slowly. The output seems to be following this input.
Yeah.
Output is just following, it may be inverted, non-inverted, doesn't matter, but it is following the input at that speed without any delay, right? As an electrical engineer, we need to understand what this limit is. Up to what point can I push the sinusoidal frequency, after which this amplifier will not be able to follow my input as fast, right? And that will lead us to some sort of RC, capacitors and resistive networks, right? And we will understand the delay in the next lecture.
Sure.
Thank you.
Thank you.